yesterday we left off with talking about this thing called state functions, and again, all of you arrived back here today. Did you take different routes? Yes, but you're here, and that's kind of the bottom line. Now, what was the way that I told you? What's the cheat method of figuring out by simply just looking at it if you know if it's a state function? The delta. The delta tells you right off, boom, I'm a state function, period. You don't have to think about it. And then work and heat or not. And so then I gave you this little example because sometimes understanding is kind of hard. So a heater and a fan are hooked up to the exact same, well, not the same battery, but an equal battery. Can that single battery put out a certain amount of power? So they're doing a certain amount of energy exchange, right? Is the fan and the heater using the same energy in the same way? No, because the heater is putting out nothing but what? That's it. But the fan is doing heat and what? Work. But do you agree that the delta E is the exact same? Yes, okay. And so that's what a state function is. It's the state function is the total change in energy, but heat and work, they can be different values, okay? So it's kind of like, I think, Peyton, I told you this yesterday, it's the good theory of life, the more work you put in, the more you get out, right? The lower your taxes are, the more money you get. Okay. All right. So we've got delta E equals Q plus W. So what is delta E? It's the amount of energy. What is Q? Heat. And what is W? Work. So if you add your heat and you add your work, is that how much energy you're going to get? Yes, Nick, put your phone up. Okay. This is important that you understand this. Have you seen positive Q be endothermic before? Very good. You've never seen that before. What have you seen positive that's endo? Which is what letter? H. So there's got to be something related here, right? So if positive Q means heat added, which is endo, and negative Q means heat loss, which is exo, do you think that Q and delta H have to be related in some way, shape, form, or fashion? Yes, and we will get to that in a few minutes. Now, this right here is why I'm glad you guys got to do those 3 POGIL activities. It's the wrong color. You can't even see that. Because this is probably one of the most difficult topics to remember is how work is applied. When work is done to the system. So if I asked you to go out there right now and change a car tire, regardless if you can do it or not, what would you be doing to that car tire? Would you be working on the tire or would the tire be working on you? You'd be working on the tire. So are you putting work on the tire? So that is a positive thing. Okay? That's input. So, and again, I guess that's another way to put. I agree with you, and actually, I like your phrasing better. So, do me a favor, out to the right here, write the word input. Work done on the system is input. Well, think about it in a relative term. Would the tire really do some work back on you? Yeah, it really would. It would force some energy back into you because when you start spinning that thing, it's going to, to break the bolt, you got to put a lot of energy in it, right? And so work done on the surroundings, which would you be considered the surroundings? Yes. And so what would negative W be? Output. Very good. Okay. So those are the two. You've got input and output in terms of work. And they're going to be different signs. So now this is where it gets a little weird. What is that big blue word underlined there at the top? Gases. There are 2 qualities that gases have to have. What are they? And? Very good. So P and V. These are the 2 things that all gases have to have. Now, if I put you in a chamber and I increase the pressure on you, are you going to feel those effects? Yes, okay. So if the volume doesn't change, then the pressure can go up and down, but the amount of work can also stay the same as well. So when you have P and delta V, how are P and delta V related in a movable chamber? Very good. So how are they related? Indirectly, inversely. So when the container gets smaller, what happens to the pressure? It increases. But we need to discuss this to a deeper level. You can know that all day long. Very good. So if we've got a bunch of, and again, I'm just using X's for particles. How many do I have in there? 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, and 7. Let me ask you my first question. Some of you may know this. What is the name of that thing when all of those X's would stop moving? Absolute zero. Very good. Do we know have we ever gotten there? No, we're really close. So my question to you is, since we don't have absolute zero, does everything on this planet move? Everything. So do you agree that these x's can be moving? Here's another question. Do they have the same velocities? This is a trick question. What is the velocities dependent upon? Temperature is equal, and this is the key word that everybody always leaves out. Everyone always leaves that part out of it. We did a warm-up a while back that had different molecules with different shaped lines. Do y'all remember that? And was every line the same on those molecules? No. They have different velocities. And what's one other factor that does affect your velocity? James, or not James, but Cody, if you and I are racing, what's going to affect our velocities? Our mass, right? So if these are different gases, would that yield different velocities? So how do you know the energy? It's the what? It's the average kinetic energy. If the temperature goes up, what are all of the velocities going to do? They're all going to go up. So what's the average also going to do? They're all going to go up. So do you see how it's kind of directly related? So, but the problem is, what happens when you decrease the volume? What happens to your area, or your volume, essentially? It gets smaller. So what happens to the amount of room they can move in? Okay, it gets less. So my final point to this, what is pressure? It's energy released by, colliding? How many L's are in colliding? Sorry. No, I totally forgot about that. It just ruined my day. I was so pumped. So pressure is going to be the energy released by colliding molecules. Well, think about this. If you have less room to run around, what are you going to do more of? You're going to collide more often. So it means the pressure has to go. So, and I use this example a lot. So if you guys are running around here, now my first question: if I told you that you were all running in here, would you all be running at the same speeds? No, Devin's probably going to be running the fastest. Okay, but if we did it in molecular terms, who would be running the fastest? The smallest person. Very good. And it doesn't make sense, right? But the lightest person would be running the fastest. I would be running the slowest because I'm probably the most massive person in here. I mean that in a negative term. I'm saying I'm blobby. Okay. So because of that, but could we have an average kinetic energy? Yes, we would take the average of all of our velocities and figure out what it is. But if we were all running, would we be colliding into each other? When does a direction of a molecule change? When it hits something else, right? Now, could we change by using electrical energy and stuff like that? Yes, but we're just talking about normal molecules. But what if I took everybody and I reduced you to the office? You've reduced volume, so collisions have to go up, right? So pressure also increases as well. So when we're talking about pressure and volume, this is why it gets a little bit weird. So when work is positive, is that input or output? That's input. And I think, and Jacob, you're the first person to ever make this make a little bit more sense in my brain as well. You're putting work in. It's input. You're adding it to it. Okay? So here's the weird part. When you put work in, what happens to the volume? If I took a balloon and I squeezed on it, what's going to happen to the volume? It's going to get smaller. What is that process called when the volume gets smaller? Compression. Okay, so it's kind of a physics term as well. But if you think about just literally grabbing a balloon and pushing on it, now some of the air is going to come out, but we're going to compress that thing. Well, what happens when work is done by the system? What does it mean by the system? We're talking about output. So that means that the balloon is pushing where? In or pushing out? The balloon is literally pushing against the universe, right? We think of that in weird, strange terms, but in the balloon is completely different than outside of the balloon. Well, what's outside of the balloon? The universe. Okay, the universe is outside of this balloon. And so when the work is being put out, the balloon is trying to expand. It's trying to get bigger, so the volumes are going to be changing. So how are pressure and the volume related? Again, they're different. They're indirectly related. So that's why pressure in gases is a little weird. So if you think about this, the initial state and the final state. So my first question is, what happened to the volume? It from A to B, and this from left to right, what happened to your volume? It increased. So what happened to your pressure? Your pressure decreased, okay? So your area changed, that's the wrong button, by that amount, okay? So if your area changes by something, you can figure out exactly how much your pressure is going to change. Now, you physics people should remember this. Pressure equals force divided by area, right? Y'all use it? Really? So, and I've talked about this before. So let me use this as an example. Peyton, hold up your hand. Do like this. So let's pretend. Do you agree that she has a specific area of fingertips? What am I applying? What am I applying specifically? Am I applying a force or pressure? I'm actually applying a force, right? Okay. Now, go to one finger. Go to the. See, this is what happened. What have I done to this? What has changed? The area has decreased. If I apply, stop, sir. If I apply the same force, does she feel a different pressure? Yes. So force is applied, pressure is felt. Force is applied, a pressure is resultant. So you feel different pressures. So think about this. When you think about atmospheric pressure, how many of you have ever flown before? How many of you have ever flown? Okay. When you fly, what happens to your ears? They pop. Why? The pressure changes. So, is there a force on your eardrums? What are you feeling the effects of? The pressure change. So again, a force is applied, a pressure is an indirect relationship to that. Does that make sense? Yes? Exactly. So the lower this number gets, if the F stays the same, what happens to the pressure? If the area gets smaller, which I went to less fingers, but I applied the same force, the pressure's got to go up. Now, what happens if I apply too much pressure to one finger? It breaks it. But what happens if I apply the equal amount of force to four fingers? You have more stability there. Okay, Mary, you were first. I don't know the answer to that question. Yes. You're reestablishing equilibrium to a degree. He's really not making this up. He's being for real. Exactly. Yeah. Even though the cabin is pressurized, it's still losing pressure because of the altitude. And it's enough to be. Imagine if you were outside the plane. It'd be even worse. And and that's a funny question. People say, "Well, chew gum." I think what you're doing is the eustachian tube is allowing the movement of the tubes, and it's actually popping your eardrum for you to equilibrium or equalize it. Yeah. It is. I hate it. All right. So work at a constant volume. So here's the thing. If volume is constant, what's your delta V? 0. Like if your volume does not change. Give me a real life example of a constant volume thing. A steel box. Doesn't move, right? We're not talking about balloons. We're talking about steel boxes. Can a pressure inside of a steel box increase? Yes. One way and one way. Oh, well, there's two ways. All right. There's three ways. Altitude. I wasn't thinking about altitude, but altitude. Add stuff to it. Why add stuff to it? The number of moles of molecules, the more collisions you have. What's the third way? Heat it up. Very good. So there's three ways. You can change your altitude, add more stuff, or take stuff away, heat it up, or cool it down. So those are really the three ways that the volume stays the same. So do you agree that we just saw this formula just a second ago? Work is equal to the negative pressure times the change in volume. If there is no volume, look at this. If there's no volume change, what is negative P times 0? So what is W? So you have no work. So if your volume does not change, can any work be done? No. So work's not being put on the system, nor work is being given off of the system. So, and here's the interesting part. We solved this formula just a few minutes ago as well, right? The amount of energy we have is equivalent to the amount of heat and the amount of work we put in. So if the volume doesn't change, you just told me that W was 0, correct? So if W is 0, then what can E be equal to? Exactly. So the amount of energy is directly related to what specifically? The temperature, the heat, the amount of energy. Okay? So in a constant volume system, and the reason we're getting into this is because we're going to be talking about something called calorimetry. And calorimetry, and we've done one of these labs, is where you're measuring the amount of heat exchange between two objects when they react. And so, remember the little coffee cups that we used? Yes? Okay? We'll get there, okay? So, this is the important thing, is that the amount of energy is directly related to the heat that is either offered or given off. Okay? All right, so here's what I need to do. A system releases 125 kilojoules of heat while 104 kilojoules of work is done on it. Calculate the delta. You guys are intelligent. I've given you the formulas in white. Calculate it real fast. You tell me. Everybody take it. You can literally do this without a calculator in your brain. But I'm going to tell you that I have a feeling that several of you are going to be wrong. But I'm okay with that. But if you got it right, we're going to have high fives here in just a second. So you told me that when a system releases 125 kilojoules of heat. Now my first question is, where in the world do I plug that in? Okay, I plugged that in as a Q. So it's 125 kilojoules, right? And then it's plus the amount of work. So I put in a certain amount of energy and I did a certain amount of work, right? So I did 104 kilojoules of work, correct? So what is that going to be? What is my total? Okay, so 229 kilojoules. But here is the part of why you're wrong. Very, very good. The key part about this chapter, and this is why this chapter is hard, is because of this word right here. You read right through it. As soon as you see the word releases, what changes about this? What turns negative? 125 turns negative. So is 229 right? No. So not only is that wrong, there's also another thing we have to take into account. How is your work being applied on it? Is that input or output? Input, positive or negative? Positive. What if, hypothetically, it said it was output? Then it would be negative. So now, what is the correct answer? Thank you. So the correct answer is negative 21 kilojoules. Negative 21 kilojoules of energy. That's why this chapter is difficult. Because you read it as numbers and not as values. Okay? Because in physics, how important was your signs? It was pretty dang important. Were you negative or were you positive? And this is very important. This is very much like that. So see if you can do the bottom one now. And read it for value. Yes, sir. I was going to give you a high five. I owe you a high five then. Very good, though. Very good. Uh-huh. 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 Brain teasers. Yeah, you may need a calculator on this one. Use your phone. Just use your phone. So what's the first, wow, that's ridiculous thought? Liters to milliliters. Now, I'm going to go ahead and tell you, whenever we're doing a lot of these calculations, I want you to think of units in R terms. And what do I mean by R terms? No. Gas and energy R's. What's your gas R unit? Latum over molk. What is your energy R unit? Come on, guys. Joules per molk. So whenever we're working with gases, what are the two units we want to get them in? Liters and atmospheres. Latum. Okay. So we've got liters and milliliters. So which one do we want to convert? Let's convert that to liters, which would be what? It's got to go three places to the left. 1, 2, 3. Now, that may be a little bit harder for you to figure out. So what is your delta V? So we've got equal negative P, which is 2 atmospheres. It is a repeating decimal. So what's your change in volume? Negative 0.4995 liters. Why did I say negative? Yeah, final minus initial. So from 5. Hold on. From final minus initial. That's final minus initial, right? Yeah. So what is it? Negative 4,995 milliliters, right? Which is 4.995 liters. Okay. Yeah, negative. So I wrote the number wrong. My bad. So 4.995 liters times 2, which gives you about what? So really technically it was 3 sig figs, 2 sig figs, 2 sig figs, so 9.9. 9.9. Latum. Now that's very important. 9.9 latum. Liters times atmospheres. By what? Yeah. I don't know. There's not a derived unit of that, is there? I don't think so. All right, so calculate delta E for a system undergoing an endothermic process in which 15.6 kilojoules of heat flow and where 1.4 kilojoules of work is done on the system. See if you can figure this one out. You may want to go back and look at the other one for just a second. I can't stress to you how important the signs are going to be in this chapter. Signs. S-I-G-N-S. What? Yes, we're going to get there. All right, so I'm pretty sure you guys got this part right. You know to add them together. You know where the numbers go. But my question is, I need signs. This says endothermic. Now, this is good news because that's a lot easier to remember. So if it says endo, what does that mean? That's going to be positive. And then it says heat flows and we're 1.4 work joules is on the system. So is that input or output? Input, so that's positive. So this was a little bit easier. So what is going to be your delta E? Okay. No. No. Yeah. Okay. So 17 kilojoules. 4 plus 6 is 0. Yeah, so it should be 17 even, but remember we're plus or minus 1. And you came up with 28? Oh, okay, she goes to 1. That's right. Okay. All right. This is probably the hardest one. See if you can calculate this one. This is probably the hardest one. This is exercise 3. Shh. Read it in your head. This is probably the hardest one. There's a lot going on in this one. Huh? Mm-hmm. Yep. There's a lot going on in this one. But these are the kind of problems, if you can do these, you can rock on through this chapter. We'll get you there. All right, so here's the deal. And Devin, I gave you this hint. Devin, what I say your hint was? Label. So here's my question, Devin. I'm going to propose this to you. What is L and L? Liters, which is a what unit? Volume. But it says it changes from this to this. So it's volume. So really what's going on here? Delta V. That's what I'm looking for. So this is your delta V. Okay, so I got a delta V. By the addition of 1.3 times 10⁸ joules of energy as heat. Heat is what? Q. Assuming that the balloon expands against the constant pressure of 1 atm. So I've got a P. And then notice what it says. Calculate delta E. And then it gives you a little conversion factor. We'll do that in a second. So they gave you a delta V, a Q, and a P, and asked you to calculate E. Well, here's the problem. We had two formulas. I promise I'll come back. So we had delta E is equal to Q plus, thank you. And we also had W is equal to negative P delta V. Well, the problem is we don't know specifically W, right? But can we calculate W? Yes, okay. Now, they tell you that W is equal, in the pressure change, the pressure was what, 1 atm? Okay? So the pressure was 1 atm, and what was the delta V? 0.5 liters, right? No, because they canceled because it was a delta, right? Is it? No, that's right, because you can't get, that's division. My bad, I was thinking of dividing. So really, it's 5 times 10 to the 5th, right? Okay, 5 times 10 to the 5th. No, I moved it. I moved it. You're 0.5, I'm 5. Either way, you're still going to, you should get the same answer. So, which is negative 5.0 times 10 to the 5th liters. Put it in that. Thank you, man. NHS. So, now what do you do with this number? Plug it into W. You want to join us again, Jordan? Ah, thank you. I'm so glad you just said that. So this is Latin. So, but the problem is work needs to be in what unit? Joules or kilojoules. Okay? Yeah. So the problem is they gave us Q in joules, and then they tell us that 1 latum is equal to 100.1.3 joules. So what do we have to do to this number? Okay, so I'm going to just do it right here. So this is 1 latum is equal to 101.3 joules, which tells me I got how many joules, so ignore this. How many joules? Seriously? 50,600,000? 5.1 times 10 to the 7th. Because she said 50,600,000. Correct? Okay, so 5.1 times 10 to the 7th joules. Okay? 5.1 times 10 to the 7th. Now, so here's my question. What is the sign on your work? Negative. So what is that? Is that input or output? Output. Go back and reread it right here. It says assuming that the balloon what? Expands. What is the balloon doing? It's pushing on the outside world, right? It's pushing on the universe. And so is that output? So does it have to be negative? Fantastic. Good. Just want to make sure that was concurrent with what we're talking about. Now, help me out. What was the Q again? Endo or exo? What does it say? It says by addition of energy as heat. So it's got to be positive because it's endo. All right, so we've got positive. I forgot the number. 1.3 times 10 to the 8 joules. No, it can be in joules or kilojoules. Okay, and then we've got negative 5.1 times 10 to the 7th. Let me erase all this. 57 joules. Okay. Why did I forget? There's a plus in between there. So you have 1.3 times 10 to the 8 joules plus a negative 5.1 times 10 to the 7. I understand you can just subtract, but I like to make sure my signs stay with the numbers. So what is the final answer? Garrett, you got it? So that's the final answer, 7.9 times 10 to the 7th. Now, since this is already in scientific notation, is it appropriate to leave it in this? Yes, if you wanted to write it in kilojoules, you can, but it's just going to make it no different. What's the exponent going to change to? Move it 3 places. 4. It'll go down to a 4. So really, you're not changing anything but the exponent and adding a k. So just leave it like it is. Really? I'm moving it? You just divide it by 1,000. Yeah, I'm with you. Yes, ma'am. Okay. So I have a positive number plus a negative number. This is a larger number than the negative number. Yeah, to the 8 to the 7th. Does that make sense? Yes, sir, Devin. Yes, sir. Yes, sir. Yes, sir. Okay. So if you do 4.0 times 10 to the 6th, excuse me, check. Let's redo this. Do you agree that delta means final minus initial? And read, this says from this number to this number. So this is final and this is initial. So it's 4.5 times 10 to the 5th, times 10 to the 6th minus 4 times 10 to the 6th, which leaves you 0.5 times 10 to the 6th. Right? But I put it as 5 to the 5th. I just moved my decimal. Does that make sense? So if you go back and you look, the reason that you could write it as 0.5 to the 6th. That's perfectly fine. You're going to get the same answer. I just went ahead and moved it to the 5th. That's the only difference that I have. Okay? All right. Let's see what we got next. So more terms. So again, system versus surroundings. So a system, this is what you're going to focus on. So it's a beaker on a table, a beaker on a table in a room, a beaker on a table in a room in a classroom, a beaker on a table in a room in a classroom. So it's whatever you're going to focus on. And the surroundings is literally everything outside of that. But where are we really mainly going to stop our focus? The beaker. That's it. That's where we're going to stop. And it's basically how it's going to affect everything. So the system is either going to give off energy or do what? Again, that's it. There's no other options. The system will either pour energy in or it's going to give energy off. So, and here's the interesting part. If the system gives energy off, what type of reaction is that? Exothermic. If the system takes energy in, what type of reaction is that? Endo. Is there going to be a temperature change for that? Yes. Will work be done to do that? Yes. So that's how it does not get any simpler than that. Okay? We already know these terms. Endothermic is absorption of energy. The energy is a reactant. This is the extension. This is the way that you already know that.
And again, it says the things get cold. Exothermic is a release of energy, and energy is a product. And again, in delta H is positive, delta H is negative. These are the things that you already know. If you like highlighting things and circling things, the thing that I would highlight here is that an endothermic energy is a reactant and an exothermic energy is a product. Those are the two things that I really kind of want you to focus on in terms of how we apply endo versus exo. So again, same products. Notice what's happening. What are our two specific reactants in this molecule? Okay, so we've got nitrogen and oxygen gas producing what? Be specific here. How many? 2 moles of nitrous oxide, right? So to make this happen, what has to happen from energy? It has to be a big. So do you agree that we are adding energy to do what? Add E to make bonds. Because we've talked about this. In all of chemistry, where does energy come from? Bonds. That's it. That's where it comes from. But look at the other one. What can anyone tell me what specific compound CH4 is? Methane. What are you reacting it with? Oxygen. What are you producing? Carbon dioxide water. So this particular reaction is what? This is combustion. Haven't we already learned that all combustion reactions are exothermic? So, what are we doing to those reactants? We're breaking them. But when you break them, what's happening to the energy? You are releasing energy by breaking. I gotta get a new clip for this. You're releasing energy by breaking bonds, but here's what I always get. I always get this follow-up question. You get to breaking bonds in the combustion reaction, but are you also forming new bonds? What are the new bonds that are being formed? The water and carbon dioxide. I'm saying, well, how can you break bonds and make bonds and still give off energy? So, does it release more than it is required to make? Yes, prime example. If you have a credit card bill of $100 and someone hands you $200, what happens to the other $100? You keep it, you save it, or you can spend it, you can release it, right? So do you have extra energy to play with? Well, what do reactions do when they don't have to spend all their energy on something to make something? They release it, they get rid of it. Okay, same concept, it's released. Okay? Yeah, but you are right, you should say it. Okay, so this is kind of a weird thing that we need to talk about, and hopefully you know at this point, but I put this in here to reiterate some very important things. You should know STP. What does STP stand for? Standard temperature and pressure. Here's the difference. Is there a difference in STP and standard conditions? Yes. The way you can think about it is think about if this were a room. You would not want it to be 0 degrees Celsius in this classroom, right? So when it says STP, it's completely different than standard lab conditions. So you've got 25 degrees Celsius. So 77 is much better than 32. Now you say 77 is hot, but it's better than 32. Okay, it's better than the alternative. So you have solutions of 1 molar. And how do we symbolize standard conditions? The not symbol, the little degree looking symbol. So instead of them having to state what's standard, they drop that little not symbol in and they're ready to go. Okay? Now this is one last little thing I want to talk about too. Y'all, I kept begging you last chapter when we calculated delta G, it wasn't just joules or kilojoules, it was joules or kilojoules of what? Per mole of reaction. This is copied and pasted directly out of the curriculum framework, which you are tested upon. There has recently been a change of how enthalpy, entropy, and energy are units are expressed. For example, you may see delta H naught values expressed in kilojoules in older printed material. Currently, this is how it has to be. Kilojoules or joules per mole of reaction. Now why? You can go read this article if you want to read it and understand it, but we're not getting into it. Just accept it as a fact. This foliage requires certain things that you don't understand or know why, but you do them anyways, right? Same concept here. Just accept it as what it is. Would you agree that these two trends in nature are true? Just look at it for just a second. Would you agree that they're true? Okay. Pile of leaves. How many of you have to rake yours? Terrible thing, right? Okay. That's how I'll do it too. I'll just vacuum it up with one more. But how weird would it be if the opposite happened? It would be amazing, right? So, Does it require a whole lot of energy to knock those leaves out of a pile? But does it require a whole lot of energy to put them back into a pile? So the forward reaction would be what? Pile to scattered or scattered to pile? Pile to scattered is forward. Is this TF or is the reverse TF? The forward is TF. So this is going to be the natural progression of things. But we're trying to relate this to entropy. So what does nature prefer? Big stacked piles or just leaves everywhere? Leaves everywhere. That's what nature prefers. Nature prefers things to go from order to disorder, kind of like your life, right? Seems to be going along right, and all of a sudden just like shit hits the fan and it just goes by, right? Okay, I don't care. But that's what's happening. Last thing, imagine if you lit a match and it never went out. Okay? Doesn't happen, right? So high energy to low energy. Things always naturally progress from high to low because what's it trying to achieve? Equilibrium. Very good.